Good morning and welcome to this session of the MIT Fire Hose Chat. I am Carol Urbano, your host from the MIT Museum. Former MIT President Jerome Wiesner once said, getting an education at MIT is a lot like drinking from a fire hose. Fortunately, today we're just going to take a sip from that fire hose and get a taste of the work of Amos Winter. He is the PI for the Gear Lab here at MIT and a professor of mechanical engineering. And now I'm going to turn it over to Dr. Winter. Welcome.
Great. Thank you, Carol, for that introduction. And it's a pleasure to be with all of you today, this morning, this afternoon, this evening, wherever you are. All right. Well, let's go ahead and get started. So I'm going to tell you a bit about my work designing products for developing and emerging markets. And I chose this as an intro slide because I think it really nicely captures the ethos behind what my research group does. This is a picture taken about a year and a half ago with a pilot desalination system to remove salt from water that we set up in India with a corporate partner, Tata Projects. And so you have me in the background here and some of my students and then some of the Tata Projects engineers. And so we're never designing technologies really for, we're designing technologies with partners around the world as well as the end users of those technologies. So to start out, I just want to reflect for a second about why I think about specifically designing products for developing emerging markets, and why might that be different than designing for, say, the US European market? Well, I think what's interesting is that you can look at metrics of human health and well-being, particularly throughout the developing world. And an example of these metrics are the Sustainable Development Goals. These were put out by the UN, the United Nations, in 2015, and they're all goals to try to achieve to do things like reduce poverty, reduce hunger, provide water and sanitation to people, et cetera. And what I think is interesting when I look at these goals as an engineer and a product designer, you very quickly realize that some of the challenges behind these goals do not affect us as much in wealthy countries as they do people in poorer countries. And what's interesting about that as a designer is it means that there are solutions available to solve these problems, but for some reason they haven't migrated over to poor countries. And the reason is, I think, is because of a price-performance mismatch. So if you think of any family of technologies, let's say automobiles, they're going to lie on a nonlinear price performance curve. So maybe up here you have like Ferraris and down here you have like Toyota Corollas. But you can change features, change designs to move up and down that curve. So what I think is interesting about poor countries is that people there are still going to demand a reasonable level of performance. You know, nobody wants a semi-functional water purifier, or a semi-functional toilet. But the price point they can afford may be different and lower than what we pay in a wealthy country versus in a poor country. And what I think is interesting about this view is that if there's no way you can adapt an existing technology to move down this curve and hit that required price and performance point, there's no way you can meet those needs of a poor country with existing technology. So somehow you have to think of another way to do it. So what my research group does is 3 stages of how we try to solve these problems and create products for global markets. First is we really try to understand the market constraints and requirements, both from a technical and socioeconomic standpoint, to really understand what do people need, what do they desire, what would they pay for it, and so to understand this intersection point. The second is we leverage what MIT is best at, which is science, engineering, research, as well as good, rigorous product design, to give us disruptive insights to understand how could we leap off this existing technology curve to that price performance point demanded by an emerging market. And then finally, we don't just focus on poor countries, we try to think about how could we grow a whole new line of new technologies out of this new price performance point and sell them to poor and rich countries alike through this process of reverse innovation. So we can make one product family, sell variants in wealthy countries, sell variants in poor countries. And so I cut my teeth doing this with first designing this product, the Leverage Freedom Chair, which was initially designed for developing countries. in situations like this. This video was taken in rural India. And we realized that people also wanted a high-performance, low-cost, rugged wheelchair in wealthy markets. And so that enabled us to start a company called Global Research Innovation Technology, which now very successfully sells a US variant as well. So you can see, same kind of DNA behind both products, but they're each customized for their individual market. So today I'm briefly going to tell you about a few of the projects in my group that represent these three areas of how we go about designing products for developing and emerging markets. The first is about a type of desalination to remove salt from water. It uses a technology called electrodialysis. The second is our work on low-cost, passive, high-performance prosthetic feet. And then I'm going to wrap up talking about our low-pressure drip irrigation work. So to start out, just going back to this idea of elucidating new markets and really understanding socioeconomic constraints. When our desalination work started a number of years ago, we could have taken a very tech push approach. We could have said, okay, we know there's dirty water around the world. We're going to make a water filter and we're going to solve the problem. But the issue with that approach is that we wouldn't necessarily understand what are all the market requirements and constraints that would have to be met for a successful solution. So instead, we embarked on a rigorous detective case to understand what are the contaminants, how does it affect people, what opportunities exist to solve this problem, and what would be economically viable. And what came out of that investigation, initially in our target market of India, was realizing the most prevalent contaminant of water is salt. So anywhere where you see a color other than blue on that map, the water is not safe to drink because it's too salty. And as we dug in more, we realized that, boy, the communities that are most affected by this often don't have grid access to electricity. And we realized, boy, where there's a lot of salty water, there also happens to be a lot of solar radiance or solar power available. That's what this map is showing. And we started partnering with an industry group that told us, there's been a lot of attempts to make solar powered desalination, but it's just too expensive because of the cost of the solar panels and the batteries and the power system. And so digging into the technology space, we realized that, well, when we look at the industry standard, which is reverse osmosis, versus other technologies, principally being electrodialysis, we realized that for the salinity ranges you typically find in India, electrodialysis can cut your energy in half compared to reverse osmosis. And why that's important is that when you go off grid, it cuts your energy system cost in half, that solar power system. Furthermore, we realized that electrodialysis wastes a lot less water than reverse osmosis. And so the point of this story is by putting together this rigorous detective case, we saw this disruptive opportunity for electrodialysis being a viable potential desalination system for India and in other portions of the world that have brackish groundwater. So as we dug into this further, we started designing systems that could purify the water using electrodialysis, and we ended up winning a prize competition from USAID a number of years ago, and then we followed that up with doing field pilots in many different parts of the world. And the moral of the story here is that understanding market requirements isn't just an upfront activity, it's an ongoing iterative activity. So by doing this work, we understood people's user requirements, price points, what would it take to make a viable solution? And so a big lesson that came out just from this first pilot is that it costs a huge amount of money, $63,000. The ED unit alone, the stack, was about $40,000. And in comparison, what we were competing against was on-grid reverse osmosis, which was about $5,700. So we had to somehow tackle this order of magnitude difference in price. And so through a number of years of innovations, what has come out at this point is a technology that is price competitive with reverse osmosis. And so our newest technologies are solar powered. This is a picture of our newest, what we call time variant desalination systems. And what's really unique about this technology is that typical electrodialysis will run in batches. And this sawtooth pattern is showing the batches you would run throughout the day if you designed a solar powered desalination system using a conventional design process. And what we said is we realized and invented a method of changing our power consumption of electrodialysis to match the rise and fall of the sun throughout the day. So with this trick, We can operate in a short amount of time, make a huge amount of water, reduce our batteries, and pull all these tricks to reduce costs. And so this plot on the right is showing how the cost of our newest technology stacks up with reverse osmosis. So this is what current electrodialysis would look like, how much it would cost in the sawtooth pattern, and this is our newest innovations. And you can see that now we're hitting price parity with on-grid reverse osmosis. And why that's particularly exciting is the cost of our system includes the cost of the power system, which is the solar panels and batteries. So this is looking like a very promising solution that could be used throughout rural communities that face challenges with brackish water, and be affordable at the price point that's already affordable for these communities, which we know from on-grid RO. The second project I want to talk about is the Jaipur Foot project, where we're trying to redesign the most widely distributed prosthetic foot in the world, which is called the Jaipur Foot. And it's been successful over the years because it looks lifelike. So if you go to a temple, you don't stand out for being disabled. It's flexible, but it's really too heavy. It's handmade, so it varies a lot in product quality, and it's really not compliant with international standards. Furthermore, people in developing countries and throughout the world want to look able-bodied as they walk. And this is particularly important where there's still a lot of stigma against disability, which is the case in India. So if a person looks disabled, they might not be able to get a job or get married or fully integrate in society. And so, the main story here, and this goes to the second point in my intro, is leveraging engineering science and product design to create that new disruptive solution. And what we did is we were the first group that was able to connect the mechanical design of a prosthetic foot to its biomechanical performance. So we could make a low-cost foot made out of plastic that bent as you stepped on it and allowed a person to move very naturally as they walk with our foot. So what that looks like in space and time is here's a person taking a step, and here's it overlaid with what that foot would actually look like on a person. And this video was taken with a test subject of one of our feet in India. But again, going back to that point of understanding unique market requirements and user needs, we couldn't just make a foot that looks like this hunk of plastic. We had to make a foot that looks lifelike. And so we also had to consider how could we overlay and bond over our supporting structure of our foot a cosmetic covering that makes it look like a normal, able-bodied, natural-bodied foot. And so over the last couple of years, we've worked actually with the world leader in hiking boot manufacturing, Vibram, to make a variant of our foot that has this foam over mold and basically a hiking boot sole on the bottom, high wear, but still lifelike looking sole. And this foot costs only tens of dollars. It's very, very low cost versus feet that perform as well cost thousands of dollars in the US. And we just recently finished a field trial of this foot, and it's worked quite well. It didn't degrade. It enabled people to walk faster through like various terrains, walk faster on flat ground. And on a 0 to 5, what's called a Likert scale, when we ask people their feedback on how they rate the foot, our foot scored higher than what is the standard right now, the Jaipur foot. So we're quite excited, and we're actually doing a big effort right now to bring this to commercialization because it works quite well. Then finally, to wrap up, just to touch on our irrigation work, which I think really represents trying to tackle multi-market, really global technological and product opportunities, is that if we look throughout the developing world, there's 2.5 billion smallholder farmers who, if you want to change their lives, the biggest impact you can make is enabling them to irrigate, because they can grow more and higher value crops, make more money to rise out of poverty. The issue is traditional means of irrigation require flooding the field, like is shown in this picture. And that's a real problem in water-stressed regions like India, where already they're getting close to running out of water. And already globally, 70% of fresh water is used for agriculture. So we couldn't just take hundreds of millions of farmers and have them start flooding their fields. There's just not enough water in the ground. So the potential like silver bullet type solution here is drip irrigation, where you just drip out the exact amount of water plants need. You can grow more crops than if you were feeding the plants with rain, and you can cut water usage by about 60% versus these traditional flood irrigation methods. And as far as a global market opportunity, this schematic shows by proportion of area how much cropland there is in the world versus how much of that cropland is irrigated with this blue circle. And the pun intended, drop in the bucket, this little red dot, which is how much drip irrigated land there is. So we realized that if we can grow the market for drip irrigation, there's huge potential for growth. And so there's a great business opportunity and humanitarian impact opportunity behind this. So the innovation behind my group really comes down to managing the pressure of the drip emitters. So most emitters run at about 1 bar or 1 atmosphere of pressure, same amount of pressure, different units. And this schematic of a drip system shows pulling water from a pond, moving it through a pump, and distributing it on the field. And the issue that this high pressure causes is that you need a lot of pumping power to move the water through the system. And it results in about a $3,000 per acre system if you want to go off grid. So what my group has done is really dive into the detailed nitty-gritty mathematics and fluid mechanics and solid mechanics of how these drippers behave. We've been able to cut the pressure required by about 10 times at the dripper, and as a result, cut the capital cost in half, and then depending on what subsidies you have, make it affordable for poor farmers. And so the message here is that through science and innovation, we're able to create technologies that can engage poor farmers in developing countries, as well as farmers in places like California, where they also use drip irrigation. This is really a global product. And another important message from our group is we don't just do this on the benchtop. We don't just do it in theory. We also do it in practice to really measure the impact. And so these are results from now a multi-year field trial that we've been conducting in Jordan and Morocco, where we've tested our drippers versus conventional drippers and showed that we can reduce pumping energy by about 50%, in most cases, which can cut the capital cost of a solar drip system by about 40%. So massive, massive savings. Or even if you're running on the grid, cuts your energy costs in half. So that concludes this short presentation, and I'm really happy to take your questions now. Thank you very much for listening to me.
Great, thanks so much, Amos. On Zoom, you can use the Q&A pod to enter your questions. And one of the things I do encourage folks to do is if somebody has already asked a question that's similar to yours, just upvote theirs or maybe add a comment that allows us to know what part of it you're interested in, okay? So I think it's really interesting that, I'm not sure if you're aware of this, you actually showed a screenshot of the UN Sustainable Goals during your presentation. And the North Anglia schools, in addition to having a collaboration with MIT, they also have a collaboration with UNICEF. And many of the students who are on here listening today with their teachers are working on sustainable goals in their schools in their own way. And they use lots of different processes depending upon the school to decide which one they work on each year. And so I'm really interested in this question from our folks at St. Andrew's International School in Bangkok, where they're talking about there are so many different problems in developing nations. And how do you find the problems that you want to work on or that you can work on? How do you make those very difficult decisions about honing in on problems?
That is such an excellent question, and one that I think deeply about. The way I frame it is there's kind of 3 areas of merit that all have to be covered for me to take on a new problem. So the first is it has to have problem merit. I'm not interested in, say, going to one village and making one gizmo for that one village, because the impact I can make is rather small. I try to seek out problems that are technical in nature, that can affect, ideally, millions to billions of people in a profound way. And so that is why we're working on irrigation and water and prosthetics. These are all millions to billions of people problems, which you can tell from my presentation has a technology aspect to it. So we do the detective work to really quantify what is the problem and what would better look like. We try to understand, okay, if we're going to make a change on these people's lives, how much would that change be? And how can we quantify it so we know our targets that we're chasing after? And that sets our design requirements that we're trying to satisfy. The second part of it, though, for me, is the problem has to have technical merit. And what I mean by that is it wouldn't make sense for a person like me, I think, given my background and my knowledge, to take on, say, a policy problem or purely a financing problem. That's not my area of expertise. I'm a mechanical engineer. I work in engineering science. And so I need to see, does the problem have some meat to it as far as creating new technology and leveraging my skills? And then as an even deeper level, I am an academic. So my core output is knowledge creation. And so we want to tackle problems that nobody knows how to solve. So we have to generate new knowledge to solve them and but at the same time create technology that can solve the problem. And then the third element that I always have to think about is value merit. So to make sure a solution can actually be disseminated at scale and sustainably, it has to align with the value propositions of many stakeholders. You have to understand things like, why would a farmer buy an irrigation system? What is the return on that investment? How do they make more money? How do we appeal to that need? We have to understand, how would a manufacturer make money? How would the technology be distributed, and how would that distributor make money? And I often question my own value merits behind these projects because, am I trying to do it to make a humanitarian impact? Is it an entrepreneurial activity? And so I really try to map out that value landscape and try to find problems that, okay, yes, we can tick the boxes and there is a compelling value proposition for all the stakeholders that are positioned to determine success or failure of a project.
Interesting. I love that you mentioned the stakeholders. Can you talk a little bit about stakeholders in these developing markets that you work with? And do they approach you with problems, or what is your relationship with people in the local market?
So one thing if there's maybe anything I can impart on you in this talk, it's the most powerful thing you can do as a designer is recognizing your own ignorance. So I could come in and say, I'm a professor at MIT, I must know everything. And that's totally bull. That's not true. And so I have to recognize that I'm good at math and engineering and at design, and I get to work in this very innovative, creative environment. But I don't know what it's like to live every day as an amputee, trying to work as a farmer, say in India. I don't know necessarily what it's like to try to make drip irrigation products and sell them globally. And so what we try to do in our projects is map out that whole landscape of stakeholders that all exert pressure on our eventual technology and will determine its success or failure, and try to map out what would their requirements be that must be met for a successful solution. And also try to map out our ignorance space. So, we're good at math and science, but how do we learn about finance? How do we learn about manufacturing? How do we learn about distribution? And most importantly, how do we learn about how this product would actually be used in real life by the end users? And so in our design process, and actually from the beginning of projects, we don't do this as an afterthought. Right from the beginning, often typically before we design anything, we gather that stakeholder feedback, we build up this team of different knowledge perspectives and bring them together and put them into the design process. So we're always driving a solution towards what we think or hope is a viable solution space. And that's an iterative process too. This is why we do field pilots, to check ourselves to see if things are working correctly. And just as a wrap up of recognizing your own ignorance, the other thing I want to impart on you is, I would say, the most powerful and important facet of being a designer is gaining perspective. The only reason designs fail is because requirements weren't satisfied. And it's often hard to see the full requirement space from your own perspective. So what great designers are able to do is be able to see from the perspectives of other key stakeholders. And this is something that folks like Steve Jobs were excellent at doing, because he could imagine a person deriving value from something like an iPad before an iPad even existed. So if you can actively put yourself in a position to see a problem from as many perspectives as possible, you're going to position yourself for success.
Thank you. So we have a couple of questions specifically about the foot. And so I was wondering if you could talk a little bit more about that. And they're more around, waterproof? How does it interact with the human body? Are there ways to have it be more of an extension of, is there sort of physical and connection with the wearer?
Absolutely. And I appreciate that question. And I'd love to talk for an hour about this foot because there's all sorts of crazy things we can do with it. The big innovation and really the scientific contribution behind that project is the ability to take a person, given their body weight and body size, and understand how they want to walk and be able to customize and optimize the structure and the stiffness of foot to enable them to walk that way. So our theory enables us to like account for, like overweight people or maybe people with smaller feet, people who want to walk faster or slower. And it also enables us to optimize feet with different materials. So, to your question of the integration with the rest of the body, absolutely. We, in the optimization process of how we design the structure of our foot, we're predicting all the loading and motions through the whole prosthetic limb and how it connects to the rest of the body to facilitate very close to able-bodied motion and loading on the body. So you have symmetry between the loading between your legs and symmetry between the motion of your two legs. And as far as the customizing it to people's needs, what's really exciting about this project is we can look at all different types of architectures of feet that we can explore. And so the one I showed you is our developing world, really low cost foot, which is super ruggedized. You can wear it in water. It's totally waterproof. It's really low cost. But we're also starting work on 3D printed feet. And what's exciting about that idea is that a person could walk into a prosthetics clinic. They could be measured by the prosthetist and weighed. That data can be put into an optimizer that we design. We can generate a foot topology. We can print it, and it can be installed on the person in one day. So in one day, they can walk in, get a foot designed exactly for them, and walk out. And so this is a very exciting thing that we're now interacting with prosthetic limb prescription clinics about because they're excited about it. It's a totally different way of prescribing prosthetic limbs, and it enables us to do things that aren't really able to be done right now, in that you can think of a person maybe after a traumatic injury initially wanting a foot that promotes stability so they can walk slowly and they feel really secure, but as they heal and as they become comfortable, they can get more high performance feet that enable them to walk faster. We could make feet that almost work like orthodontics, where you go into your prosthetist every few months, you get a new foot, and you could do more functions with it. Or we could think about doing that with like kids as they grow up. They can get different size feet on a really rapid schedule. So we're really excited about how this theory is opening up opportunities. And another message I want to convey is that, to that first slide I showed you in generating a new price performance curve of a new family of technologies, we're seeing with this baseline technology of how to design feet, we're able to design these super rugged, low cost, high performance feet for developing countries and super high performance customized feet for maybe the US European market. And actually a lot of this work has been funded by the military for high performance feet for soldiers or veterans that want to be active. And so when you get that insight of how to design that new family of technologies, it's super exciting to see the different variants you can create.
Mm. Yeah, that's a really interesting question. We have a lot of students who are really interested in affordability. So how do people in these markets afford this? Is there a way is it automatically low cost? Or if you look at this model with the 3D printing, can I really, as my child is growing, can I really, afford a new foot a year or whatever when they hit growth spurts? How does that model work?
So a major misconception in design for developing countries is that you have to make things that are cheap or low cost, and that is a artificially imposed constraint. What you have to do is align value propositions. So people in poor countries have less money than people in wealthy countries, but it's not that they have no money. And so take, for example, our irrigation project. A lot of our work is doing predictions of how we can design an irrigation system and predict a crop productivity and thus predict revenue to the farmer, and then be able to compare that back to the cost of the irrigation system, while also accounting for, say, lending strategies, interest rates of if a farmer gets a loan to buy that irrigation system. And by doing that, the system may be expensive, but if it makes the farmer a lot more money, it's still affordable, particularly if they're getting a loan. And so you see this all the time in developing countries. There's nobody, as far as I know of, making like cheap televisions to sell in developing countries. Although if you go to most poor households, they're going to have a television, even though as a fraction of their income, that television is exorbitantly expensive. It provides a lot of value, and that's why they buy it. We've seen the same dynamic in cell phones. The fraction of income that goes into a cell phone is going to be higher in a poor country, but the value they derive is really high, and that's why people invest in it. And so we have to do that economic modeling and see what technology is going to fit, and go back to that value proposition or value merit matching I was talking about. And so to your question, Carol, with the 3D printed foot, I agree with you. It's likely not going to be the beachhead market's not likely going to be poor countries. It's probably going to be wealthier countries where the foot is covered by insurance, right? Mm-hmm. We can do it there. But what we can do, though, in poor countries is still leverage the same technology, still produce a very high performance foot. And part of our research is actually looking at what increments of sizes and stiffnesses do we need to make our feet so we can best engage the full range of people that would use it in developing countries and still offer that really high performance and quality of life, even though we have a discrete number of foot sizes that we offer, like a range of shoe sizes. And we're able to do that. And that's, again, is an example of diving into the engineering science behind this, because we can predict how to do it. We can quantify how to do it to achieve the best result.
Great. Thanks so much. So we have one student who's really interested in how your work has changed during the COVID crisis. And since so much of your work is really focused on working with people in emerging markets, how are you continuing to move your work forward in each of those areas?
Oh, I appreciate that question, because this is a major challenge for us right now. We're taking, I'd say, a multi-pronged strategy. So in the near term, so over the last 2 months or so, it's not very difficult for a group like mine to go into kind of a holding pattern where we focus more on our analytical or computational work that people can do at home and with their individual computers, and writing work. So we publish academic papers all the time, so we can get those out the door. But yes, if this, as this crisis goes longer, it is very difficult for us to not be able to travel. And so what we've relied on and will continue to rely on is still this network of stakeholders and partners that we have around the world, from whom we can still derive information and feed that into our engineering work and still try to make the best configuration possible of our technologies. And I'll give you an example of that. We had initially planned over this past spring to go do a number of focus groups and farmer surveys and interviews in Kenya on our drip irrigation work. And we're going to use that information, put it into our design work, and try to improve our technology. Now, we can't do that now. And what that made us realize is actually we can spend more time right now kind of predicting the best architecture of our drip system that we can right now, given our limited knowledge. But we have done field work before, so it's not totally limited knowledge. Try to refine that the best we can and end up making what we term a looks like and works like model. And you can kind of think of this as like when you go to a car show and see that new sexy concept car. It's not really a car, you can't drive it, but it gives you a sense of what the car would look like. We can do that with our products too. And we can have one that maybe like shows how much water it outputs, that would be the works like model, and one that kind of where a farmer could hold a pump and see like, yeah, this looks pretty robust, but it's not really a functional pump, but they get a sense of what it would be like. So our plan now is that we can take those products, hopefully in the fall, to East Africa. They're not a fully working system, but when we use them to do focus groups and farmer interviews, it gives us even better feedback about the technology, because it gives us a good platform to start the conversation, to say, okay, here's what we think would work best. Well, what would you think? what features would you add? What would you modify? And it will generate, I think, even more valuable information than if we had gone this past spring, because we wouldn't have had that talking point of the looks like, works like models in front of us. And I think actually the delay in this case caused by COVID-19 will actually result in a better product, because it's changed our iteration scheme of how we design. So we're trying to be nimble and we're trying to be creative, and that's an example of a help. But an example of a hurt is we can't do clinical tests right now on our prosthetic feet with a collaborator in Chicago. And so we're still trying to be creative about how we get around that. And I think what we're going to keep chugging on is we're working on the next, what we think is going to be probably the pre-production variant of our developing world foot, which requires a lot of computer-aided modeling, a lot of analysis, and we can do that right now. So that's what we're shifting our focus on.
Great. We have so many great questions. It's so hard to choose. And I usually do take some via phone. So I'm going to let Indrani ask their question aloud.
Great.
Hi. First of all, I would like to appreciate your incredible work. I'm really, really, really so happy to see, the work especially for developing countries. And I would like to ask you, what is the percentage of side effects of prosthetic knee, and is it cost effective?
Well, one side effect you have to be careful of in all prosthetic feet or knees is repetitive strain injuries, where if you develop like a really pronounced limp and you load your legs unevenly, you can develop issues in your sound leg, your leg that does not have an amputation. And that's an example of one of the motivators behind our prosthetic foot work, because we can very deterministically and quantitatively and predictively design a foot to try to make an even load balance. And that is what we see with our feet, actually. So we certainly try to address that. And that's another example of end user and like prosthetist feedback of additional requirements that are important for us to consider in our design process. And I'm sorry, I forgot the second half of your question. Can you say that again?
Oh, I'm sorry. I already muted Indrani. But if you want to throw it in the chat, we can come back to it. And I do have two more questions. I know we're nearing the top of the hour, and I want to be respectful of your time, but I have two questions for you that really circle back to what students and teachers can do to contribute to this process. So the first is around what kinds of activities or experiences do you think teachers can create or students can kind of pursue on their own that might help them to build skills or awareness of issues that might benefit from specific product design focused on emerging markets? And the second is about role models and who really inspired your work in your pursuit of this kind of research.
Sure. I'm going to finish my answer to Indrani's question. Thank you for putting it in the chat. She asked, is it cost effective? And cost is certainly a major factor. And this is one of the reasons why we work with partners like the Jaipur Foot organization. I didn't mention them or didn't talk about them specifically, but I showed their product, the Jaipur Foot. And so, from them, we understand what are the price points that are affordable and can be adopted in the market and try to design to those. And so that's an example of a driver that led to the embodiment of the foot I showed, where we have our central load-bearing structure in the foot and then this overmold of the cosmesis. And all of that together is about the same price as what a current Jaipur foot would cost, but offers a lot more high performance and can be made in an industrial process. So cost effective is really important. But again, I want to stress that point that cost effective doesn't mean cheap. Cost effective means aligned with the value proposition and what would be affordable by the market. And it's important to always investigate those effects. So to answer your questions, Carol, so the first one about what students can do and start training. I think, I think learning about problems is one of the biggest things you can do to start off. And this goes back to the recognizing your own ignorance part of being a designer, is that, the more you can immerse yourself in a problem, and the more you can understand the different facets and nuances of a problem, the more powerful you are as a designer. I can't tell you how often I see brilliant ideas that are not solving the right problem. People drive a solution and create a solution and then go see if it fits a problem. And following that process makes you more dependent on luck than diligent design in engineering. So if you can assess a problem up front, then you're better positioned to design to it. I think as far as recognizing your own ignorance too, I never ever want to stifle ideas. I want you guys to be thinking of the new groundbreaking disruptive ideas, and do that hand in hand while realizing, I'm still young, still learning a lot. Particularly if I want to go into the technology space, maybe I need to learn more about engineering. But I still have this drive, and I'm investigating, and I'm thinking of these creative ideas. I'm documenting them down, and I think any good design comes down to comparing great ideas with the actual metrics of performance that would have to be satisfied to constitute success. And I'll give you a very relevant example that I see constantly right now with COVID-19. There's a lot, particularly a month or so ago, there's this big push to make low-cost ventilators because people saw on the horizon we're going to run out of ventilators. And a lot of groups came out with these low-cost ventilators. But it's very hard to not kill somebody if you're going to pressurize their lungs. And industrial ventilators have all these checks and safety measures on them, so they're safe for people. So just making a machine that can put pressurized air in somebody's lungs doesn't mean it's a viable ventilator. And so why I'm saying this is that it is tremendously valuable, and I encourage you all to be creative and strive for these novel and great ideas, but take the time to evaluate them against the metrics that would constitute success. So you don't end up launching an idea, God forbid, that hurts somebody, but you also best position yourself to launch an idea that's best positioned for success. Then to answer the second part of your question, as far as inspirations, I think for me, one of the biggest inspirations is actually a guy named Louis Pasteur, who invented the process of pasteurization, which is how we make sure milk and other fluids are clean. We can kill bacteria by briefly heating them. And what I love about Louis Pasteur is he was a hardcore scientist and researcher, and made great advancements in the understanding of disease and pathogens and germs and all this stuff. But he also had an eye on the applied space and was thinking about, how can I make an impact on society with this? And a guy like Louis Pasteur, his innovations literally improve the lives of billions of people a day. Like anybody who's drinking milk typically is benefiting from him. And so this ethos of hand in hand striving to tackle real world problems where you can make a profound impact in the world, while also advancing science and understanding and really utilizing that scientific tool as the enabler to create the new solutions. That's what excites me. And a great book on this is called, I think it's called The Idea Factory. It's about Bell Labs. And it tells a very similar story about how the transistor was invented. And again, it was like Bell Labs saying, hey, we need to improve telecommunications. Let's hire a bunch of physicists. And they came up with the transistor. The physicists won a Nobel Prize. And telecommunications were changed forever in the world. So those are good inspirations for me.
I'm sure most of our young people can't imagine life without a transistor.
Yeah. And I want to add one more thing. My two personal heroes as engineers, this isn't developing world necessarily, but are the Wright brothers. Because to me, they are the kings of experimental science, because they started with, right around the turn of the century, the prevailing knowledge of flight was wrong, how wings worked. And in the period of 4 years, they took this insurmountable problem of how to make an airplane, broke it down into small chunks, solved each chunk one at a time, lift, control, propulsion, put it together, did it predictively to be confident their plane could generate enough lift to fly, put it together, and it basically worked on the first shot. and they didn't have any college education. They did this on their own time in their spare time, and arguably made the greatest technological innovation in human history.
Great. One of the questions, let's see, we do have, one question we have, two, I'm going to kind of put them together. One is, what do you see as your greatest contribution so far? And then the other part of that is, what problem do you want to try to tackle next that maybe isn't on your current list?
I think, I guess my greatest tangible contribution so far would be the wheelchairs I showed in one of the intro slides. And that has turned into a company. It's sustaining, it's improving people's lives, and that makes me very happy. But I feel a self-consciousness about this because the global markets of developing world wheelchairs have changed over the last decade, and it's made it much harder for an independent manufacturer like us to sell in the developing world. Most charities now that distribute wheelchairs make their own chairs. And so I don't think that product, even though we've done a couple thousand of them in the developing world, it's not had the level of impact that I wanted it to. And I've really taken that lesson, particularly into our prosthetic foot project, to really clearly up front make a global strategy of how we can do very large impact at large scales in the developing world, as well as the rest of the world too, make high value products. And I'm very much doing that. I think with the three technologies I said today, they are all on the cusp of going to commercialization. And so I think the impacts behind them now are really the deep scientific and engineering insights that we've created that's shown us this path to disruption. Where we in all of these situations, actually, we took what could be regarded as very stagnant industries where there hadn't been huge changes for a long time, went in and saw where to cut out like 50% of the power or make a super high performance foot with plastic, and like really big changes. And I think that is a contribution in itself and an achievement. But what excites me is seeing those move forward through the next few years where we're very strategically plotting their course to large scale dissemination. And I will feel good when there are, hundreds of thousands of feet out there and thousands of our D-cell systems and, millions of our drip emitters being used by farmers. That would be gratifying to me. As far as looking at what's next, sanitation is an area that is very interesting to me because, it's about, there's over 1 billion people throughout the world who don't have access to like a reliable toilet, which is crazy. And that has huge impacts on human health. And so we're doing some groundwork to think about where could there be a niche that we could get involved in. I think in my career, if I think about like the next 40 years or so, issues around climate change are something very motivating to me. And I think about how in a technological role like I'm in an innovative environment, how could I make an impact really around probably carbon capture and mitigation? Because if you look at the targets to stem global temperature rise and the reductions in carbon outputs that we'd have to achieve, we're not at all on track to do that to the United Nations goals. And so I think we're going to need probably a coupled solution in both the policy space and technology space. And that is the type of problem that really appeals to me, where it's multifaceted and you have to understand these socioeconomic aspects as well as technical aspects and blend them together to see at that intersection where do you have opportunities for improvement. And that blending process is how we have created all of our technologies thus far. And I'm hopeful that if we can do it, in the climate change space, we can also get insights to where we could make a big impact there.
Final question is kind of on the commercialization side. It relates to both. I'm kind of merging two people's questions. One is about, since you're in academia, but you are also working in conjunction with both private companies and NGOs and local stakeholders, who kind of owns that intellectual property? And then as you're going through this process of scaling up, how do you make affordable things while also making money?
Yeah, so this is a great question. To answer the IP question, intellectual property invented at MIT is typically owned by MIT, but a sponsor and company would get the first rights to license that. So, and they can do it exclusively. So, in effect, it turns out to be like if they owned it. But let's say they don't want to use it, and it gives MIT the ability to maybe license it to somebody else. We try very hard to, when we do the mapping of the stakeholder space, understand organizations that have a successful track record selling similar products to what we want to invent, and that know the market really well, because we want to learn from them, from their market insights, and also they can be a viable conduit through which we can disseminate our technology and they can make it. There are some situations, though, where we want to do like a startup company and commercialize it ourselves. So we're always kind of assessing that. But by and large, if it's something, say like drip irrigation, where you need a huge amount of infrastructure to just make the product, it wouldn't make sense for us to start our own drip irrigation company. But going to the point of profitability, again, that comes back to the point I tried to make earlier about, even poor people have money to spend, and they are making good decisions, or they are always making decisions about how to allocate their resources. And what it comes down to, I think, is matching value propositions, like I said before, where you want to create, ideally, a product that people want to buy and need to buy. And this is a misconception oftentimes in international development engineering, where we try to design products we think people need, but if they don't perceive wanting them, they may not invest in them. And so we're always trying to align wants and needs. And we're always trying to do the financial projections of how is this technology affordable. And so, that includes capital costs and what people are willing to pay, but it also includes return on investment for something like an irrigation system where they're literally making money off it. And so I very much and vehemently feel this way, that making money off of technology is not mutually exclusive with having a humanitarian benefit. That is a major misconception in development work all the time, that people think you need to give away technologies or it has to be ultra cheap. That's absolutely not true. And actually, that's a detrimental mentality oftentimes, because let's say each of our drip irrigation systems costs $1,000 and we want to get them to 1 billion farmers. That's $1 trillion investment, right? And if you think about $1 trillion charitable investment, forget it. It doesn't exist. If you think about $1 trillion market opportunity and revenue opportunity for a company, oh my God, companies are super excited about that. So if you can set up the dissemination of your technology through free market mechanisms, you naturally create an incentive to scale and sustain the dissemination of the technology. And that is what we're always trying to do. Now, mind you, we can't always do it. So the prosthetic foot is an example. The global market for low-cost developing world prosthetic feet in developing countries is all done through charities. And we have to recognize that. There's no market demand to sell a foot to that customer base, because the families with a disabled family member are going to say either, oh, we could spend money on this foot, or we could just go to this charity and get a free foot. So the free market mechanisms are killed. They just don't exist. So instead, we have to figure out how can we align our technology with that charitable mechanism, as well as the manufacturers that make the foot, so they can still make a product at the price point that would be afforded by the charity. So it's complicated, but again, if I can impress anything on you, it comes down to matching value propositions. If you could do that and incentivize everybody to adopt your technology, you'll be in the best position.
Right. All right. I'm going to take one final question from Hassini.
So this question is about, so can you apply your design? You have, right now you have talked about your new prosthetic foot design. Can you apply it, your design for making prosthetic legs for children for the ages 6 to 10?
Yes, certainly, Hasini. What we're able to do is when we have a target walking behavior we want a person to achieve, we are able to scale the loads on their feet, the forces on their feet, and scale the motions of the movement relative to their body size and body weight. And that can certainly be scaled down to a child. One of the big merits, I would say, of our technology is that we can do those kind of more outlier type cases of, creating limbs for people who are very heavy or very small or very short. And actually, one of the motivations behind our work was actually demanded by the US Congress in order to make improved prosthetic limbs, particularly for women who oftentimes have to use limbs that were made for men that are too big or too stiff for their body weight. And so we can very quantitatively account for all of that and design a specific foot for the individual, pretty much no matter their body weight or body size.
It's great contribution to the field. I'd like to thank everybody for joining us, and thank you, Dr. Winter, for sharing your work and your inspiration with our students. They certainly have a lot to think about as they take on next year's UNICEF challenges. And we will
Can
be—
I say one thing to that, actually?
Yeah, sure.
So I know we have an audience from around the world, and I could tell by accents of people asking the questions that they may have grown up outside of the U.S. I don't know where you're living now, but one maybe word of advice I can give to you is that to become, I think, the most powerful next generation of designers is, particularly if you want to change lives in your home countries, if you can keep that local perspective and remember the local context that you grew up in, so you really understand that local population's needs and requirements and what would change your life. If you can combine that with your educational training, so you can get, let's say you eventually get a PhD from MIT and you're super high technically trained, that combination of skills will make you a world changer. And I always recognize my lacking in those skills. I grew up in rural New Hampshire, so I don't know anything about what it's like to live every day, say, in rural Africa. And so I'm always trying to compensate for that knowledge gap. But if you can somehow combine your local knowledge with hardcore educational training, you will be unstoppable.
Thank you. I'm not sure there's much more I can add to that for sure. We invite all of you to keep your eyes posted for our next in our series of Fire Hose Chats, which will take place on Wednesday, May 27th. And thank you to Cambridge Science Festival and British International School of Boston and North Anglia Education for supporting this ongoing work. Thanks very much, everybody, and look for the recording on Global Campus and other social media outlets, including Facebook Live and the MIT Museum site. And have a great day. Thanks again, Dr. Winter.
Thanks for having me. It was a pleasure.